Given this triangle, find the coordinates of point A using angle C and any other given variable. Before we begin, when I'm looking at this triangle, I put it on an XY coordinate axes, and we have our same similar setup that we have angle A, B, and C, and so we have little a, little b, little c opposite those. The coordinates of point B are going to be a comma 0, since a is the x length, and then it's on the x-axis, so it's 0. Now we need to find the coordinates of A. What we can do is draw our altitude down, draw our auxiliary line, because what we need to do is find x and y. X will be the horizontal piece and y will be the vertical piece. How can I do that using angle C? I can say let's say it is for the x coordinate, we can say cosine of C equals x over b, or in other words, x equals b cosine of C. Similarly, we can say sine of C equals y over b, which would give us b sine of C equals y. That means we know the coordinates of this point, A. It is b cosine of C, comma, b sine of C. And that's part A. Now remember that our original triangle ABC is not a right triangle. We made a right triangle in there so we could come up with these calculations. Now let's take a look at the part B. Find the length of AB squared, and then simplify it completely. Well, AB squared is this length here, and we can call that C squared. That is a part of this right triangle. I know the length y, and I know what x is, but I do not have the other length, the length here from the perpendicular to B. But can I figure that out? Yes, since the whole length is A, and I know this first part is x, this second part, going from there to there, will be A minus x, or in other words, A minus, what was our calculation for x? B cosine of C. Now that I have that, I can use the Pythagorean theorem and say A minus B cosine of C, quantity squared, plus our y squared, and y is B sine of C, quantity squared. Now we need to square this out. Remember, this is the same thing as saying x minus y quantity squared. So we will have little a squared minus 2 times the first times the second, 2ab cosine of C, and then plus b squared cosine squared of C. Remember, it's a cosine that's being squared, cosine of C, that quantity is being squared. And then plus b squared sine squared of C. Now we're asked to simplify this. Is there anything that you see? What you can do is pause it for a second and try to figure it out yourself. Okay, let's assume you've done that. I see here that I have a sine squared and a cosine squared, and they both have the same coefficient. So I can factor that out and to get cosine squared plus sine squared. And we know that from our identities, that is just 1. So what we can do is, let's just rewrite these other things on down. We have a squared minus 2ab cosine of C plus b squared, or in other words, a squared plus b squared minus 2ab cosine of C. Now what we want to do is understand what this is saying. what's really nice about this, again, is this works for any triangle, and I'll go over some more of that in just a second. Does it look familiar to you at all? What if we covered up this last part there? We have a squared plus b squared equals c squared. Well, that's our standard Pythagorean theorem. What we want to do anytime we have something new is let's see what's going on. Let's understand what's going on. So in order to do that, let's look at some different situations. So first I'll say basically what's going on in this part is dependent on this angle C. So let's look and see, what if angle C equals 90 degrees? Let's move this up so you can see it. Well, we'll have C squared equals a squared plus b squared minus 2ab cosine of 90. What's the cosine of 90? You're thinking, oh, this is a unit circle. Yes, that is 0 degrees. The point would be 0, 1 on the unit circle. So we get our a squared plus b squared equals c squared. And that agrees with what we already know. That's our Pythagorean theorem. Now let's see. What if this time C is less than 90 degrees? Let's take a look on something like this, and I could say here's our angle C, and we still have A and B. And as far as this one goes, let's assume as we're going through this that the A and B's are the same length for each one of these situations. And then we have something to compare it to. Because if we change the side, it won't necessarily make sense as to what's going on. Well, what would you guess about this opposite, the side opposite angle C compared to this first one? When we have a squared plus b squared equals c squared, we have this hypotenuse. It's no longer hypotenuse because it's not the right triangle. But if I take, and this side A is moved down, it would seem that little c is getting smaller. Let's see if our equation agrees with that. C squared equals a squared plus b squared minus 2ab cosine of c. Well, since c is less than 90 degrees, cosine of c is what kind of number? Well, less than 90 degrees, and it has to be greater than 0 degrees. It's in the first quadrant. All of our trig functions in the first quadrant are positive, so the cosine of c is positive. A is some positive number, B is some positive number, cosine of c is some positive number. So what we have here is c squared equals a squared plus b squared minus some positive number. Well, what's the effect of this? That's going to be making it smaller. So c is smaller compared to the right triangle C. So our equation agrees with what we think should happen when we're just looking at the picture. Let's see what happens if C is greater than 90 degrees. So on a problem like this, again, we're going to try to leave B and A the same. We have B, A, and little c. There's capital C. So when we're looking at it this time, we have C equals a squared plus b squared minus 2ab cosine of c again. And when I put that the C is greater than 90 degrees, we should also have at the same time it has to be less than 180 degrees, right? Because you can't have an angle in a triangle greater than that. So what quadrant are we dealing with there? We're dealing with the second quadrant. So the cosine of C in the second quadrant is less than 0. So now let's look at see what's going on. We have a squared plus b squared minus 2ab times what now? Actually, we can even take away that. We know that 2ab is a positive number, but this time a positive, and a negative, that result will be a negative number, so we'll get a squared plus b squared plus some number. Now what it's telling us is that C is going to be longer compared to the right triangle C. Now when we did this problem, I labeled this ABC. But there's no rhyme nor reason about that. We could have labeled this A at this point and then C over here and B there, or we could have labeled this B and C and A. So what that's saying is the actual positioning of those letters is not so important. We could repeat this with any of the sides. Well, what would happen? Okay, well, let's do this first. Let's write this formula using find A using angle B. We could also think about it as rotating it around. What's this going to be? Well, instead of before we wanted to use angle C, and now what we're going to do is use angle B. When we look at our formula, we have C with the cosine, and then we have little c on the opposite side. So if we're going to be using angle B this time, we're going to have little b on the opposite side. And then at the end over here, we'll have minus 2 blank blank cosine of B. Well, if I have B that's being used now, basically the C and the B you can think of as being switched. What we're going to have here is a squared plus c squared minus our 2ab, or 2ac, sorry, cosine of B. And what would we do if it was a squared first? It would be a squared equals b squared plus c squared minus 2bc cosine of what angle this time? A. We can rewrite this in general. Instead of actually labeling sides, we can label an angle. So if we call this angle theta, this would be the opposite side. This could be adjacent side 1, and this could be adjacent side 2. So what this would be is opposite side squared equals adjacent side 1 squared plus adjacent side 2 squared minus 2 times adjacent side 1 times adjacent side 2 times the cosine of theta. Now note, it doesn't matter which one's adjacent side 1 and which one's adjacent side 2. Now what is this? This is the law of cosines. And it works for any triangle. And that's it.